This is steady state. A circuit is in this steady state if currents and voltages are all constant in the circuit. If currents and voltages are all constant in the circuit. Circuits with inductors and capacitors in this state can be analyzed using previous techniques by replacing the inductors with short circuits, we mentioned that, and capacitors with open circuit. So you replace inductors with short circuit and capacitors with open circuit. And I remember that in the previous classes we've had, where I've explained to you how to replace circuit elements with short circuit and how to replace them with open circuit. So we'll try to bring that again to play in this particular discussion. So don't forget, for in the DC state, a circuit is in DC state if the currents and voltages are all constant in the circuit. In the previous discussion we had for the AC circuit, the AC discussions that we had, we said that the currents and the voltages are supposed to be continuous, depending on when if you're talking about capacitors or inductors. For inductors, the current is supposed to be continuous. For capacitors, the voltage is supposed to be continuous. But in the DC state, the current and voltages are constant in the circuit. All right, let's go ahead. So here is a simple example to quickly, bring to memory how to short a circuit, open a circuit, and then find missing elements or values in our circuit. Assume the circuit is in DC steady state. Find the current I and then find the voltage V. So this is the current I, and then where's the voltage? This is the voltage V that we're looking for. So we're looking for this I, and then we're looking for this particular voltage. What we find here is that we have two inductors. This is inductor 1, this is inductor 2, and then we have one capacitor here. In this steady state, we assume that we short circuit the inductors and then we open circuit the capacitors. If you do that, what you would find or have here would look exactly like this. For the inductors, we short circuit them. You see, we short circuit it. We short circuit the inductor of 2 Henry here, the inductor of 1 Henry is short circuited here, and then the capacitor 1 microfarad is open circuited here. So if you apply KVL to the loops, okay, so this is the loop with the voltage, so we could say this is one of the loops we have, so you could use this loop, or you could say this is another loop that we have, okay, so this is another loop. So if you use this outer loop, this is the outer loop, this is the inner loop here. For this outer loop here, what you will find is if you carry out KVL, or if you implement KVL here, you have minus 36. As you can see, we are traversing from negative to positive. So you have minus 36. And then if you go this way, you have current passing through 2 ohms is I, and then the voltage here will then be I times 2. So you have plus 2I here. And then there's nothing going on here because we short circuited it. And then right up to this point. Now the current passing through, this is the current source, by the way, going up here. And the current passing through here is 2 ohms. That current cannot come through this place because this circuit, this point is already open circuited. We already opened the circuit, so the current has to just pass through this conductor and then go like that way. So if the current is going this way and this is also coming this way, total current passing through 4 ohms, this 6 amperes current source plus the I, coming from this other side. So I plus 6 will be passing through 4 ohms, and then the voltage across these 4 ohms will be 4 multiplied by I plus 6 equals 0. So if you solve this expression, what you will find is 6I equal to 12 and the I will be equal to 2 amperes. So we've been able to find I here, the I passing through 2 ohms. I is 2 amperes. Now you can also carry out KVL. KVL in this other loop, this second loop we have that has V in it. KVL here would mean we have 36 minus 36 rather, because we are also traversing from negative to positive in 36 volts. So you see we have minus 36 plus 2 multiplied by I, and our I is already 2 amperes, by the way. So you can see we have minus 36 plus 2 times 2, because I is 2 here, plus this voltage. We're also traversing from positive to negative for this particular voltage, plus this V equals 0. So if you solve these and then make V the subject, you obtain your voltage V to be equal to 32 both. Okay, so that's pretty much straightforward. That's pretty much easy. Okay, you just, you have your V, you have your I, and that solves this entire problem. Here is another example. Assume the switch here. This is a switch. You can see the time switch here. So here is a switch. Assume the switch in the circuit below has been closed for a long time. It was opened at t equals 0, time equals 0, times 0 minus and times 0 plus refer to the instant before and after opening the switch respectively. So before opening the switch, we have 0 minus as time. After opening the switch, we have 0 plus. All right, so these are times that I use to just represent what is happening after you have opened the switch or before you open the switch, or after you close the switch or before you close the switch. Okay, so let's have those. The question then says find a value for the source function Vg. Okay, so the source function Vg, we are looking for that voltage so that I of 0 plus will be equal to 2 amperes. Once we find the value for the source function Vg for I of 0 plus 2 amperes, then for this Vg that you have obtained in this first part, find V of 0 minus and V of 0 plus. Okay, so find V just before the switch is opened and then V after the switch is opened. So that's what they're talking about. So how do we deal with cases like this? Now, I must quickly call your attention to something very critical and important. And here is it. Please pay attention. Current through an inductor and voltages across capacitors cannot change instantaneously. So that simply means current through an inductor and voltage across a capacitor have to be continuous. These are things that we mentioned when we're talking about inductors and capacitors, right? So the current through a capacitor, I is usually equal to dV/dt. All right, it has to be continuous, and then current through an inductor, okay, has to be continuous, and voltage through a capacitor has to be continuous. You remember we said that I for capacitor is supposed to be equal to C dV/dt, something like that. This is supposed to be I through capacitor. So for the capacitor, this dV/dt, it has to be continuous. It cannot be constant, right? And then we also say that for inductor, our V is supposed to be equal to L dI/dt. If you still remember, L dI/dt for inductor. All right, so in this particular case for an inductor, the current cannot be constant, the current has to be continuous. If you remember, we mentioned that when we were talking about the individual circuit elements, when we were talking about the capacitor and the inductor. So for the capacitor C, as you're looking at here, the voltage cannot be constant. For the inductor, the current cannot be constant. And that is why it is mentioned here that current through an inductor and voltages across a capacitor have to be continuous, they can't be constant. So if we obey this particular law, if they are continuous, it simply means that I for the inductor, I of 0 plus must be equal to I of 0 minus, and for the capacitor, V of 0 plus must be equal to V of 0 minus, because these terms are continuous, not instantaneous. All right, so in addition, assume the circuit has been in DC state, capacitor will be opened and then inductor will be short circuited. Okay, so that simply means this is a capacitor, you open this circuit here and then you short circuit what is going on. Where's the inductor? It short circuits the inductor there. So when you short circuit the inductor, what you would have here is just going to be, you cancel it. So what you would have right up here would just be like this when you short circuit it, and then you have something like this, and then we go, and then we don't have these here anymore. When you open this circuit, what you're going to have is going to be something like this. You open this circuit here, and then this is going to be like this, and then we continue. Okay, so that simply means this is not going to be here again when you open this circuit and when you shut this circuit. If you apply KVL at t equal to 0 minus, that is t equal to just before the circuit was open, just before the switch was opened. So you have V of 0 plus, you're applying KVL. V of 0 plus will certainly be equal to V of 0 minus. Don't forget we said that V of 0 plus must be equal to V of 0 minus, and both of them will be equal to this Vg that we're talking about here. So if you apply KVL, what you would have is going to be minus VG, right? Uh, Minus VG is what you're going to have, plus, if you go from here, this is going to be a short circuit, so we cannot say anything about this. So the current is just going to go and then pass through this 4 ohm. So you have minus VG because we are traversing through negative here, and then it becomes plus 4I, right? Minus VG plus 4I, and then if we go this place, go down via the 12 volt, you have minus 12 volt here in the circuit, and then we go straight. This is open here, this is now open, so nothing happens here. We just go straight, and then the circuit is continuous like that. So if you add all of this together, it should give us 0. Now if you rearrange this, what you will find, and make VG separate of the formula, what you will find is that your VG will therefore be equal to 4I minus 12. That's what you're going to have. All right, and we already know that our I plus would be equal to I minus. All right, so and that would be equal to 2 amperes. So at T equal to 0 minus, our I of 0 minus also will be equal to 2 amperes because they would be the same based on this particular explanation we gave. All right, so this becomes 4 multiplied by 2, that is 8. 8 minus 12 will give us minus 4 volts. So you find out our VG will just be equal to minus 4 volts, just like we have obtained here. All right, so this question, I want to believe, is also straightforward, and this is something that if you go over it again and again, you can easily understand the concepts that is being discussed. Here. Okay, let's take it a step further and see what next we have for us. We have practical capacitors and inductors here. So when we talk about practical, it simply means that there are some assumptions we've been making. I'm assuming that we have ideal capacitors and ideal inductors. In real life, most capacitors are not ideal, most inductors are not ideal. So that simply means that there will be some kind of losses, and some of these losses will be based on some other kinds of parameters. For example, when we have a capacitor, a real capacitor, has leakage through dielectric, which can be modeled using a parallel resistance. So you see a resistor is connected in parallel with a capacitor. This is what happens in real life. This is what we see in real life. Okay, so you can see we have the capacitor, the resistor is connected. The resistor is connected in parallel with the capacitor here. Okay, and this is what is going to help us account for the losses that we are experiencing. Also for the inductor, we usually have very long cables, wound together in inductors. So that also makes for some kind of losses, okay, along the line. So to model, the losses for an inductor, we connect resistors in series with the inductor. So for capacitor to model for the losses, we connect resistors in parallel, and then for inductors, we connect resistors in series. Please pay attention to some of these, okay? All right, let's go ahead. So now we will briefly talk about RMS values. RMS means root mean square. Okay, the root mean square value of an AC current is the value of DC current that will dissipate the same amount of power as AC current on a resistance. We have AC dissipating power, so we are looking for a DC current that will give us the same amount of power that the AC current is dissipating on this particular resistor. Once we're able to find that DC current that gives us the same amount of power that an AC current dissipates on a resistance R, then we can call that our DC current. Okay, so the above definition is based on the principle of equating the heating effect of current calculated in both sides. So first, you calculate the power dissipated in the resistance in the DC circuit as shown in this right-hand side here. All right, so what you can see here, our VR, if you want to find this VR, will be equal to current passing through this R multiplied by the R. So you can see the current is IDC. Okay, if this is voltage, this voltage is a DC source. So you see IDC multiplied by R gives us our VR, as you can see here. Also, you can go ahead and say, since we have our VR, you can say our PDC, which is going to be power dissipated on this resistance here will be equal to VR multiplied by IDC, because power is VR, all right? And we do know that our VR is already R multiplied by IDC. So if you combine these two together, your PDC will be equal to R IDC squared. Now this is an equation you're already familiar with. It's nothing strange about this equation because we've talked about the fact that power is equal to I squared R before. In this case, we're talking about the voltage, we're talking about IDC because the voltage source is in DC. So you can see that the PDC, or direct current power, would be equal to IDC squared. Okay, so if we take it a step further, what we do have here would be VR. If you are not going to calculate the power dissipated in the resistance in the AC circuit, this is not what is going to happen. When we talk about AC, we're talking about current with respect to time, voltage with respect to time, and so on and so forth. Okay, so what you have is our VR of t would be equal to I of t multiplied by R. So that is how to find the voltage across the resistance in an AC circuit. So VR of t, because we have a time varying waveform here. So we have VR of t would be equal to I of t multiplied by R. So AC power would then be equal to V of t multiplied by I of t. We know power is equal to VI under normal circumstances as discussed earlier. So if you combine these two together, what you would have here is PAC would be equal to R multiplied by I of t squared. All right. And our I of t is usually given as our I max sine WT. Okay, W is our angular frequency, and then you can see we have WT here. You can see we have time here. So, and I max represents the maximum, the amplitude, the maximum current that we have. That's I max. So what you have here, instead of writing I of t here, we know our I of t equal to I max and WT. So if you squared I of t, that gives you I squared. That will give you I max sine WT squared altogether. That is I squared of t. I max is going to be max over R. Okay, so you can just replace that and put I max here. So you can see you have the power in the AC cycle equal to R multiplied by I max sine WT squared. Okay, so in this particular circuit, this is what you have when we're talking about the AC circuit. You can see we have V of t here. In the DC, it's just going to be V, all right? But in an AC, you have V of t because the time varying waveform. So you have I of t, and then you have VR of t. So your VT is V max sine WT for these, and then your I of t will be V max over R sine WT. So let's pay attention to these two equations and keep them somewhere because we'll use them for some of the calculations we're talking about. And our I max will certainly be equal to V max over R. And our angular frequency is always equal to 2 pi f. We know that angular frequency is always equal to 2 pi f. We know that. So we can also play with that too. Okay, let's go ahead. Where f is going to be the frequency, and then pi, you know 2. And then if you know time, you can easily find sine WT, and then you can find I, or you can find V, depending on what you're looking for. So we've talked about this P power. The DC power would be equal to R IDC squared, and then AC power would be equal to R I max and WT squared, and all of this. So we're just putting all of this together to crystallize what we just talked about. Okay, let's go ahead. So we've talked about this definition too. RMS value of an AC current. RMS value, which means square value of an AC current, is the value of DC current that would dissipate the same amount of power as AC current on a resistance. So we talked about all of this before. And then we said I squared of t equal to I max sine WT squared. And then our I RMS will then be equal to 1 over t, where t is the period. Okay, 1 over t integral of I of t squared dt. Okay, so this is going to be our I RMS, the root mean square current. Okay, that we have. So pay attention to these two: 1 over t integral of I of t squared dt. All right. And the reason we have this particular, RMS is that for sinusoidal signal, RMS value simplifies to the amplitude divided by 2 raised to power 1 over 2. Don't forget, 2 raised to power 1 over 2 will be the same thing. 2 raised to power 1 over 2. Okay, it will be the same thing as square root of 2. Okay, so if we are saying that for sinusoidal signal, RMS value simplifies to the amplitude, or amplitude divided by 2 raised to 1 over 2. It simply means that we are saying our IRMS can be equal to, amplitude is usually referred to as the maximum value. So you can say our Imax, right, all divided by Imax over root 2. That is what it simply means, over root 2. That's what it simply means, okay? Or you can say your VRMS, all right, will just be equal to Vmax, which is the amplitude, right, all divided by root 2. Okay, that is what this means. For a sinusoidal signal, RMS value simplifies to amplitude divided by 2 raised to power half, where 2 raised to power half simply means the same thing as square root of 2. Okay, so these are basic discussions. So let's take it a step further from here and see what lies ahead. So here is a simple question that we can probably just check out and try to see how this applies to some of the things we've been talking about. The root mean square value of a sinusoidal waveform. Let's quickly look at that with an example. Calculate the RMS value of the sinusoidal voltage. Sinusoidal voltage waveform with 312 volts peak value as shown on the right hand side. So the amplitude in this case, amplitude voltage in this case is going to be 312. So Vmax is 312. That's why they call it voltage peak, or peak voltage, or the peak value of the voltage. So then VRMS will be equal to Vmax, like we said, divided by square root of 2. So that will be equal to Vmax times 0.7071. 1 over square root of 2 is 0.701, by the way. So we have Vmax times this, and that gives you 220 volts. Where is 220 volts on this graph? This is where it is on the graph. Okay, so your VRMS is going to be equal to 220 volts, and then your peak value will be equal to 312 volts. Okay, the amplitude value of the AC current, AC voltage is 312, and then your V RMS will be 220 volts. Okay, so in Turkey, domestic RMS is going to be 220 volts, and not only in Turkey, in most of the countries, I know that the domestic RMS voltage level is, equal to 220 volts. So, and then even in Cyprus that we are in here. Okay, so here we have an exercise that we can easily just evaluate together. Derive the voltage division equation for a series of inductors. So let's say we have series of inductors here. We have in inductors connected in series. So you have L1 and we have L2. You could have L3 right up to the last one, which is Ln. Okay, so whatever the number is. L equivalent, like we mentioned, in previous classes, would be equal to addition of all the L's, which was L equivalent. If you want to find the equivalent inductance, so you add everything together. So that is what this represents. Summation of all the inductors from beginning right up to the end. So when K is 1, you have L1. When K is 2, you have L2. When K is 3, you have L3. So you have L1 plus L2 plus L3 right up to when K is equal to N. So this represents K equal to 1 right up to N. Okay, right up to the last inductor you have in the circuit. Okay, so this is the equivalent inductance in the circuit. Also, we know that our V is supposed to be equal to L di dt, by the way. So we've mentioned that before. So V is supposed to be equal to L di dt. So if equivalent inductance in the circuit is Leq, so our V will just be equal to Leq di of the t. Okay, so, and we already said our Leq, L equivalent is this, so we just put that here. So you have the IDT multiplied by L equivalent, which is, of course, this. We just bring that into the circuit here. This would mean that if you're looking for your DIDT, you just rearrange the equation. Okay, so if you rearrange, your DIDT will be equal to V divided by L equivalent. The IDT means that V over L equivalent. This entire stuff here means L equivalent. Okay, this means L equivalent. So pay attention to that. So if you have your L equivalent like this, so let's go ahead. Now we do know that VI represents the first voltage. So let's say I equal to 1. That means you're looking for V1. So that means V1. Let's say I equal to 1. That means you're looking for V1. Let's say I equal to 1 now. So I is equal to 1. So V1 will therefore be equal to L1, okay, di dt. That's what it simply means. If we go by the expression that we do have, go by this, if you want to find V1, all right, that's what happens. If you combine this equation with this, what it simply means is that your VI, it means that your V1 will therefore be equal to, you can see we have L1 already, and we said this is already our the IDT has been given as this particular expression here, as you can see, V over L equivalent. So L1 times V divided by L equivalent. That is going to be how we find our voltage division. So if you rewrite this, it simply means that your V1 can be equal to voltage source, if you rewrite it, multiplied by L1 divided by L equivalent. This is what it's implemented. So for voltage division in an inductor, this is what you have. This should not be strange to you because we've done something like this before with resistors. Okay, so if you're looking for L2, it becomes V2 will be equal to voltage source multiplied by L2 divided by L equivalent. V3 will be equal to L3 voltage source multiplied by L3 over L equivalent, and then the story just continues, and the sequence goes on and on like that. So this is how to carry out voltage division for series inductors or inductors connected in series. Okay, so let's keep that somewhere and then go ahead. Also, we've been asked to derive the current division equation for parallel set of inductors. Now, the inductors are not connected in series, they are connected in parallel. Okay, if the inductors are connected in parallel, this is what the circuit would look like. Okay, different current passing through the inductors, and of course the voltages will be the same. So for an inductor, 1 over L equivalent will be equal to 1 divided by L1 plus 1 over L2 if we have just 3 inductors. But if we have many inductors, it becomes 1 over L1 plus 1 over L2 plus 1 over L3 plus 1 over individual inductors right up to 1 over Ln until when K is equal to N. Okay, so that is what this represents. This represents 1 over inductors, depending on how many of them will have the summation of all of those in 1 over inductors put together. That is what this represents. Okay, so that simply means if you want to find your L equivalent here, L equivalent will just be 1 divided by L equivalent. If you just cross multiply, it will just be 1 divided by this summation here will be our L equivalent. So put that in mind. Now I will be equal to, don't forget, for our inductor, we had said right from the beginning that our I normally is usually equal to 1 over L, 1 over inductor, integral of minus infinity to time t, V of t, okay, dt. This is our I right from the onset. We talked about this. If you flip back a few slides, we talked about this already. So your I is equal to 1 over L, the integral of minus infinity to t, V of t dt. Okay. If it were to be from t naught to t, we are going to have plus V naught here. That is the initial voltage. But this is from minus infinity to t, so there's no need to put V naught here. So if this is our I, if you rearrange this, it simply means if you make just this integral of V of t dt, the subject here, this would be equal to I divided by, you divide both sides by this summation. Okay, so that means you have I over this summation of all the inductors will be equal to integral of V of t dt from minus infinity to t, if you just rearrange that mathematically. And we do know that our I will be equal to 1 over Li, our I of I. This I of I here, this is I represents current, this I represents, the series, that we have, series of inductors. So this could be 1, this could be 2, so we could have I1, I2, I3, I4, I5, right up to as many places as we go into, as many, inductors that we have. So let's say our I is 1, that means we can have I1 here will be equal to 1 over L1 As you can see here, integral of minus infinity v of t multiply v of t dt. Basically, that's what you're going to have, v of t dt. So if you rearrange that, what you will see here is we had said that integral of v of t dt is equal to this from equation 1. So combining equation 1 with this equation will give us I of I. We could say I1, okay, will therefore be equal to 1 divided by L1, all right, summation of all the inductors that we have in the circuit, all right, 1 over L1, summation of all the inductors we have in the circuit. This will be multiplied by 1 over this entirely that you're looking at here will represent our L equivalent. Don't forget, okay, this entire stuff we're looking at here, okay, will represent 1 over L equivalent. Everything you're looking at here means 1 over L equivalent. So if you say multiply by 1 over L equivalent here, it simply means that you can take L equivalent off, isn't it? So if you write that, this would mean that you have I here of I1 will be equal to I, it is 1, okay, over Li, where is my pen? L equivalent multiplied by L equivalent out of top. Okay, that this is exactly what this would resolve to. This is an important equation for you guys. And then, so what this simply means is that you can rearrange it and say your I of 1, let's say I of I right now, okay, or if you want to use I of 1, it's still okay, would be equal to, this is I, by the way, this I here is current, so we cannot even use 1. Don't forget, this I here is current, so this cannot be replaced with 1. This is the big I, not the small I. So we go to I, which is the source current now, multiplied by L equivalent. If you rearrange that mathematically, L equivalent over L1 now. Okay, so you can see that we have come up with, for the inductors connected in parallel, the current will be equal to source current multiplied by Leq divided by L1, where Leq means equivalent inductors over L1, and then you will find out that if you leave this as, you know, Li too, if you want, if you keep this as Li, this can be Li. If you write 1 here, then this becomes 1 too. So if you're using I here, you put it as I here. Okay, while if they are connected in series, what we had, you know, if we scroll back a little, you will find out if they are connected in series, what we had was our voltage. We found our voltage to be, you know, Vi will be equal to voltage source multiplied by Li divided by L equivalent. So for series connection, the L equivalent is at the denominator. For parallel connection, L equivalent is at the numerator. Okay, you will notice that this also, you know, is related to what we did for resistance back, you know, a few weeks ago, almost 3 months ago. How to find the voltage divider and current divider for resistance. Okay, so we have done the same thing now for the inductors, and you have an idea of how to deal with stuff like this now. We have an exercise here, exercise 4, that we can easily check out. We've checked quite a number of exercises. So this is the 4th one that we want to quickly investigate right now. The current through a 0.2 Henry inductor is I equal to, let's not think, is I equal to 12 cos 20t milliamperes. Okay, find the terminal voltage, find the power, find the stored energy, and the maximum value of the power being absorbed. Okay, so let's fix this quick. We do know that for an inductor, that our V would be equal to L di dt. Okay, so we know that our L is 0.2, and then they gave us current, which is the, so if this is I, we need to find the I dt. What is the I dt from this current? All right, so if you differentiate 20t, you have 20, that 20 goes to the back, so you have 12 times 20 at the back here. So you're left with cos 20t. If you then differentiate cos 20t directly, you have minus sine 20t. So if you put all those together, you would have the IDT will therefore be equal to what you have here, minus 12 times 20 sine 20t millivolt, because we still have our milli here. And then this 0.2 represents our L given to us as inductor, and this minus comes from the differentiation of cos. Okay, so if you differentiate that, that is exactly what you have, and then this gives you 0.2 times 12 times 20. This just gives you, minus 48 sine 20t millivolt as the voltage or the terminal voltage across the inductor. All right. So having done that, we can then go ahead and say, okay, what happens? How do we find the power? That should become very easy. We know that our power would be equal to VL multiplied by IL. VL multiplied by IL. Power is always equal to IV. So our VL is just been calculated as minus 48. Our IL, has been given here as 12 cos 20t. Okay, so if you multiply them together, what we have would be, you have 2 millis multiplied together will give you 10 raised to power minus 6, because milli is 10 raised to power minus 3 by word. So this is minus 3, this is minus 3 here, because in the millivolt we have milliampere here. So that will give us micro, that's 10 raised to power minus 6. This is microwatt here as the power. So you multiply this two. If you multiply this two, this is what you're going to have. You're going to have minus 288 sine 40t microwatt is what you're going to have at the end of the day. All right, now this is my purely mathematics, and this is much more like a trig function in terms of application, in terms of multiplying and expanding this bracket. This is a trigonometric function. So if you can just go ahead and brush through your trig functions, and then you would arrive at what we do have here as sine 40t. Okay, so don't forget sine 40t is the same thing as sine 2 times 20t. Don't forget. So this could be sine 2 times 20t. Okay, so it could look more like sine 2a. All right. So, and if you remember your trig function, let me just give you a hint here for some of you who have really forgot it. If you remember your trig function, sine 2a is always equal to, if you have sine 2a in the trig function. Okay, let me make it easy for myself. Sine 2a normally would give you sine 2a would normally be equal to 2. Sine 2a would be equal to 2 sine a sine b. All right, for some of you who still remember your trig function, sine a will be equal to 2 sine a sine b. Okay, this is exactly how it works. So what you can see here, it should be 2 sine a, 2 sine a cos b. Yeah, that's what it's supposed to be. It should be 2 sine a cos a. Yeah, got it right now. So this is what it's going to be. Normally, sine a plus b would be equal to sine a cos b plus sine b cos a. That's what we're going to have, right? So, but now we have sine 2a. That means you replace all the b's with a's. If you do that, what you will have is 2 sine a cos a at the end of the day. So what we have here is like, this is like, if you multiply 48 by 12, it gives you something. Okay, so I don't know what value that would be. 48 times 10 will give us 480, by the way. So 48 times 12, which should give us like 480 plus 96. Okay, so you're gonna have something there. All right, so if you have 48 times 12, we put them together like that, probably you would have sine 20t cos 20t there, which looks like sine a cos a. So that's how we got this here. All right, so and then with some multiplications, we got minus 288 here. Okay, let's go ahead. This 2 here is very important. That is what dropped this to minus 288. 48 times 12, yeah, should give us about. So if you divide that by 2, it should give us minus 288, considering this 2 we have right at the back here. Okay, so then the next part says we should find the stored energy. You know how we can find the energy in inductor? It's pretty easy. We have W equal to 1 over 2 Li squared. Okay, we proved this a couple of times ago. So what you will find here, our L is 0.2. What is our I? Our I is 12 cos 20t. So if you square this, so you have 12 squared is 144 cos squared 20t. Also, this is milli, so if you square this milli, it becomes micro here. So you have our joule, this unit of energy. Yeah. So if you expand all of these, you have our joules as unit of energy. Yeah. So if you expand all of these, what you would obtain is about 7.21 plus cos 42. Again, this is another application of trigonometric function. Okay, so you can rewrite it and then you get this here. All right, let's take it a step further. The last thing we were asked to find is the maximum value of the power being absorbed. This is very important. The maximum value of the power being absorbed. What you will find here is we have PL equals this, and don't forget our notation is that whatever you have here represents your peak value, right? This represents P max. This is our P max here. Okay, this is our P max. So the maximum value here is going to be 288. Okay, and this negative sign tells us, the side of the graph that this power is on. Okay, it shows that power. So this 288 is going to represent our P max, by the way. So let's see what we have for us. Maximum absorbed power corresponding to the expression in V is going to be 288 microwatt. Don't forget we have micro here, so it's not just 288, it's going to be 288 microwatt. So it's going to be 288 microwatt, as you can see here. The reason power is absorbed is because of this minus. Yeah, it's going to be plus, we'll say power is being dissipated. Okay, so this minus here simply means the maximum power absorbed is what we're talking about. All right, let's go ahead. Here is another example that we can address. The circuit below has a switch that opens at t equals 0. All right, it has a switch that opens at t equals 0. The condition of the circuit before the switch opens is not known. The condition of the circuit before the switch opens is going to be at 0 minus, so that's before the switch opens. And after the switch opens, we're going to have 0 plus. Don't forget, t equals to 0 minus, t equals to 0 plus. Don't forget. So we talked about these notations before. The circuit below has a switch that opens at t equals to 0. The condition of the circuit before the switch opens is not known and cannot be assumed to be steady state. Given the current through the 2 ohms resistor, where's the 2 ohms? This is 2 ohms resistor. So given the current through this 2 ohms resistor is directed downward at t equal to 0 minus, just before, and has value of 1 ampere. Okay, so that means our I of 0 minus is actually just been set to be equal to 1 ampere. That's I of 0 minus. Calculate the following parameters: 1 volt at t equal to 0 minus and t equal to 0 plus. We know how to deal with all of these, so we'll look at those and then see how we'll work on the applications together right now, and then see how that connects with all the explanations we have given before now. Okay, let's get started. The first question says find the charge of the capacitor. Okay, so you know that the charge is usually going to be Q equal to CV. Q equal to CV for the charge. All right. To find from the question given to us, we know that we have been given our C, right? Our C is 0.5. We're looking at the charge of a capacitor. So our C is already 0.5 farad from the circuit given. So what we're going to have is VC here. So to find VC, let's go ahead. Since we know that our I of 0 minus is equal to 1 ampere, so keep that somewhere. So we can find VC of O minus right now, just before, because we want to deal with T equal to 0 minus. VC of 0 minus would be equal to V2 ohms of 0 minus. So VC of here will be equal to VC of here. Why? Because these two are connected in parallel. And for parallel connections, the voltages are expected to be the same. So the VC here would be V across these 2 ohms will be V across this particular capacitor here. So, and that would be equal to, if you want to find the V across 2 ohms, that's going to be pretty easy. We know the current passing through 2 ohms, I of 2 ohms has been given to us as 1 ampere. Our I of 2 ohms will be equal to I of 0 minus, don't forget, will be I of 0 minus, which will be equal to 1 ampere as given in the question. So our I of 2 ohms, okay, across here is 1 multiplied by these 2 will give us the voltage across here, which will be the same voltage across here. So we have 1 times 2 gives us 2 volts. 2 volt is across here, so 2 volt will also be across here. And don't forget, we had said right from previous slides that VC of 0 plus will be equal to VC of 0 minus, and that will give us 2 volts. Why is this so? Because of continuity procedure that we talked about. Because across the capacitor, the voltage cannot be constant; it has to be continuous. All right, so it cannot be instantaneous; it has to be continuous. So to talk about the continuity, VC of 0 plus will be equal to VC of 0 minus. So we have 2 volts here. So since we have our 2 volts here, and then we have our C to be equal to 0.5. So we say that our charge in this capacitor would be equal to Q equal to CV. We know that C is 0.5, so we have 0.5 multiplied by our VC 0 minus will be equal to 2 multiplied by 2, and that will give us 1 coulombs at the end of the day. Again, this will be the same value for VC of 0 plus, okay, because we do know that for continuity, procedures, VC of 0 plus will be VC of 0 minus. And since 0.5 is the same for both of them, the charge will be the same for both cases. Okay, so the charge will certainly be the same for both cases. That solves question 1, the A part of this question. Now, the next thing you want to look at is the current in 4 ohms directed to the right. Okay, so the current in the 4 ohms directed to the right, coming this way, is what we are looking for right now. So how do we do that? At t equal to 0 minus, don't forget that the circuit below was opened at t equal to 0. So at t equal to 0 minus, the circuit was short, so current was flowing this way. So at t equal to 0 minus, we can find I of 4 ohms. All right, I of 4 ohms will just be equal to V divided by R, V over R, applying simple Ohm's law. V equal to IR, I will be equal to V over R. Our R is 4 ohms, and in our voltage, if you use, don't forget, we found voltage across 2 ohms to be 2 volts, right? So for series aided voltages in a circuit, you subtract them, you subtract the smaller from the bigger. So the effective voltage in this circuit is just going to be 10 volts minus 2. All right, 10 volts minus 2 volts will give us 8 volts. That is effective voltage, in this particular circuit. So that's why you see that. That's why you see that our I of 4 ohms will be equal to 8 volts divided by 4, and that gives us 2 amperes. So current passing through this 4 ohms will be 2 amperes. All right, and then what they told us to also find is the current passing through these 4 ohms at t equal to 0 plus. At t equal to 0 plus, this simply means after the circuit has been opened. Okay, after the circuit has been opened. So this would mean that when a circuit is open, current is not flowing. When a circuit is open, please don't forget, current is not flowing. So t at 0 plus automatically across 4 ohms would be current across 4 ohms at t equal to 0 plus would certainly be equal to 0 amperes. So I of 4 ohms at t equal to 0 plus will be equal to 0 amperes because the circuit is now open. Okay, and t equal to 0 plus represent what happens after the circuit has been opened. T equal to 0 minus represent what happens just before the circuit is open. That is how to deal with the A part and the B part. Then we have the C part where you're asking us to find the current in the capacitor directed downward. Current in the capacitor directed downward. Okay, so I want to presume this will also be easy to deal with if we apply KCL. So let's see what happens. Okay, so the C part, just before the circuit is open, let's apply KCL here. We have here, this is a node here, right? So we know the current, there's a current coming in here, right? And this we have been told is downward. So current coming in here, another one will go this way. So this would also be this way. So if you apply KCL to this particular, instance, what would you have if you apply KCL just before the circuit is open at t is 0 minus? So the current passing through here will be I4 ohms, isn't it? So you can say for KCL, our I4 ohms. Okay, we know that when current is entering the node, we give it negative. So we have I4 ohms plus I2 ohms, right? Plus, because these are leaving that node, I current across capacitor, addition of everything must be equal to 0. So if you rearrange this, you must find out that your IC will be equal to I4 ohms, right? Will be I4 ohms minus I2 ohms from what we have here. And that's exactly how we got this IC equal to I4 ohms minus I2 ohms. We know our I4 ohms already from calculation is 2 amperes. We did that, we calculated that, at the B part. And then I2 ohms, we calculated that too as 1 ampere. That has been given to us already in the question. So 2 minus 1 gives us 1 ampere. So IC, just before the switch was opened, IC would be equal to 1 ampere. After the switch was opened, what do we have? When the switch was opened, no current would pass through these 4 ohms. So current through these 4 ohms would be 0 after the switch was opened. All right. And don't forget these guys here are in parallel, okay, and we still have a voltage in the circuit. All right. So if no current is passing through this particular place, it simply means this is like an open circuit right now. So nothing is going through here. Right. So that is why just after we open the circuit, the current will just be the current in I minus 2 ohms. This is very, very important. Okay, so I of C, this becomes 0. You have 0 minus I of 2 ohms, and then you have I of 2 is just 1, so that's going to give us minus 1. And if you want, you can try to calculate it again, and then you have minus 2 over 2, because the volt we calculated across 2 ohms is V is 2 volts, and then the ohms is also 2, so you can use 2 over 2 to get minus 1 amperes, and then that is what we do have here with the real sense of it. So I think this solves the C part. We can then go ahead and try to solve the D part of the particular question. The D part of the question. Find the VC, the T. Find the VC, the T. VC represents the voltage across the capacitor. So we do know that our IC is usually giving us, IC here is giving us IC equal to C dV the T. We know this already. That's a current passing through the capacitor. So if you are looking for this, can be C dV C anyway. So if you are looking for this, we just make it the subject of the formula. This would just be equal to IC over C automatically. Okay, so that's what that is going to be. So dV C dt is going to be IC over C. We found I across the capacitor to be 1 ampere, if you remember in the previous questions. So then we know our C, capacitance, is going to be equal to 0.5. So 1 over 0.5 will be equal to 2 volts per second. Okay, 2 volts per second. Okay, so that's going to be the VC, the T, just before the circuit was opened. And after the circuit was opened, our IC, don't forget, it was minus 1. After the circuit was opened, we found IC to be minus 1 on the previous slide. So you have minus 1 over 0.5, and that gives you minus 2 volts per second for your VC, the T. So this is how to deal with problems like this, how to deal with questions like this in case you have to work on them in a project or you have to deal with them in an examination. Exercise C. If the circuit provided below is in DC state at t equal to 0, t equal to 0 minus, it's in DC state at t equal to 0 minus, find V1 and V2 at t equal to 0 minus and t equal to 0 plus. So if you look at the circuit here, where's my pen? Let me pick my pen up. If you look at what is happening here, you will find out that at t equal to 0, the switch is open at t equal to 0. What we would see here is that at t equal to 0 minus, that would mean the circuit was closed. At t equal to 0 minus, the circuit was closed. All right. So what that would mean is that at t equal to 0, the circuit was opened. Now at t equal to 0 plus, it simply means that there is no current that can pass through this place like this. That's what it simply means. Nothing is going on through this place upward when t equals to 0 plus. Okay, so but then before we go into all of those, let us see exactly Let us try to demystify what is going on at t equals 0 minus. Okay, so let's get started. Now, the first thing you want to do, like we discussed at the beginning, is that for the capacitors, you open the circuit, isn't it? When you open the circuit, this is what it looks like. No current is flowing through this place when you open the circuit. So what you just have here is going to be open circuit voltage, VOC, or V1. Also, for the inductor, you will short the circuit. All right. So when you short the circuit for inductor, what you're going to have is short circuit current. So that would mean that your V2 on this short circuit is going to be 0. Okay. So what you're just going to have here is going to be ISC. So V2 will be 0. But then we'll come back to that. Let's just continue. Okay. So now if you short this, have a short circuit instead of inductor here and open circuit instead of a capacitor here, how do we deal with this particular circuit? You will see that there is a current, there is a voltage source here which is 25 volts. There's current I1 flowing through to this particular node. Okay, so at this particular node, I current is going to split into the left and then to the right, and then it goes this way. Whatever current goes through the 1 ohms resistor is I2 as labeled in the circuit here. So I2 gets this node. It cannot come this way because this is an open circuit. No current will pass through here. So what you're going to have here is your current that passes through 1 ohms will go to this node and then pass through 3 ohms. So what you can say here is that 3 ohms and 1 ohms are in series, because the same current that passes through 1 ohms will be the same current that will pass through the 3 ohms resistor. Okay, so these guys are in series, and then if you add them together, it gives you 3 plus 1, that's 4. That means 4 and 1 here are going to be in parallel. All right, so if you deal with those, and then this, there's another resistance here, so we're going to deal with all of those together right now. All right, so let's go ahead. We already mentioned here that V2 0 minus will be equal to 0, since the inductor is a short circuit for the DC. It's a short circuit, so V2 0 minus will be equal to 0. All right. I1 of 0 minus now. I1 of 0 minus will be equal to, if you apply our Ohm's law, V equal to IR. If V is equal to IR, our I will be equal to V over R. So the R here would be just the equivalent resistance that we have in this circuit. How do we find the equivalent resistance in this circuit? Because that's just all we have left. All we have left here is just the resistors, and then this voltage, and then the current passing through the resistors. Okay, so if you find the equivalent equivalent resistance, that will give us, since we know these guys are in series, right? So that becomes 3 plus 1, that's 4. Okay, 4 and 1 are going to be in parallel. If 4 and 1 are in parallel, that simply means that we can have 4 times 1, 4 plus 1, 4 times 1 divided by 4 plus 1 will give us a parallel combination of this and this. So you have 4 times 1 divided by 4 plus 1 here, because they're in parallel. Okay, plus, now what you will find here is there is a 16 over 5 here. So if you combine all of these together, you are going to have just one resistor. Okay, so that one resistor, you will be in series with these 16 over 5, and of course all of them will be in series with 1. So you have 4.1 over 4 plus 1 plus 16 over 5 plus 1, this 1 ohm that we have here. All right, so that gives us the equivalent resistance that we have in this circuit. And if the equivalent resistance this is all we have as the equivalent resistance, that simply means that our I1 will just be V over R, which is going to be 25 divided by all the resistance we have here. And that's what we have here. That's going to give us 5 amps. All of these here is going to give us 5, by the way, because 4 times 1 over 4 plus 1 will give us 4 over 5. 4 over 5 plus 16 over 5 will give us 20 over 5. 20 over 5 is going to be 4. 4 plus 1 is going to be 5. So you have 1 over 5 times 25 gives us 5 amperes. Then we want to find our I2. This is I2, okay, passing through this place. So for I2, since we know our I1 going up here, so we know the source current I1 right now, so we can then find our I2. All right, it's going to be easier to apply current division to I2 now that we know our I source of 5 amperes. Okay, so I2 will be equal to I source multiplied by, we are looking for the current passing through I here, I1. So, and we know the resistance of this current we're looking for is 1 ohms. So the I source is going to be I1 0 minus that we just calculated coming out here. So it's going to be equal to I source multiplied by 1. This 1 here represents the resistance of the I2 that we are looking for. So you have 1 divided by 5. This 5 here would represent the equivalent resistance. Okay, we represent the equivalent resistance here. Okay, so we are looking for, don't forget, we found this equivalent resistance to be 5. So everything you're looking at the bottom here will be 4.1 over 4 plus 1 plus 1 plus 16 over 5. So everything you see here is what is represented with this 5, because we are working on voltage, current division. Okay, so that's why how we got this 5 here. So you have 1 divided by this 5 multiplied by the I source, which is I1 0 minus that we already calculated, and that is also done over 5. So 5 over 5 will give us 1 ampere. So I2 will be equal to 1 ampere. So the current passing through 1 ohm resistor is equal to current passing through 3 ohm resistor, and that will be equal to 1 ampere. All right, this is very important. Please pay attention to that. That is I2. Then what else again? So now that we know our I1 before the circuit was opened, and we know our I2 before the circuit was opened, then we want to find KVL. KVL would allow us to find V1. We want to know V1 now. We already know that V2 before the circuit was opened would be equal to 0. We said that already. This is V2. So how do we find our V1? We apply KVL. If you apply KVL using our notation, okay, what you'll find out if you apply KVL would be, you will find that we have minus V1, right? For KVL, minus V1, if we go and then we come here. Now the current I2 is going up, and then we have our loop current this way. So if we are going this way, this is going to be minus because we're going against this I2. So minus V1 minus I2 multiplied by 1, right? Okay, and then if we keep going down, this is going to be I2O minus, by the way, because we are dealing with what happened before the circuit was open. So you can put I2O minus, okay, here, multiplied by 1. And then if you keep going down, you get to go down this way. You can see that we have a 16 over 5 here. So this is also going to be the current going through here is positive, is going this way. So we are also coming down like that. So it's going to be minus 16 over 5, also multiplied by the current. What is the current passing through here is I1. So it's going to be I1 of 0 minus here. Okay. All right. And then this direction is traversing from positive to negative on this voltage. So we're going to have plus 25. And everything will be equal to 0. What you will find out here is that this is the KVL. So if you rearrange that, our I2 0 minus, I2 is 1. So what you have here is 1 times 1. So you have minus V1 minus 1. You have 16 over 5 here times 5. So that becomes minus 16. All right. And then you have plus 25 will be equal to 0. Okay, so your V1, if you take V1 to the other side, your V1 O minus, by the way, will therefore be equal to 25 minus 1 minus 16. That's 25 minus 17, and that will give us 8 volts automatically. So what you will find out is that your V1 here is 8 volt. This is 25 volt. V2 here is 0. And that's O minus, by the way, before the circuit was closed. And then we found our I2 O minus to be 1. We found our I1 O minus to be 0 minus to be at t equal to 0 minus to be 5 amperes. So what is left is all these calculations here are before the circuit was opened at t equal to 0 minus. So once the circuit has been opened, now we're done with what happened before the circuit was opened. That's t equal to 0 minus. Now t equal to 0 All right, t equal to 0 plus, circuit was opened. Now t equal to 0 plus, we want to find out what happens in the circuit. When t equal to 0 plus, it simply means there is nothing going on this branch. As soon as t equal to 0, nothing is going to flow through this branch. So we just take this branch out. That is why you cannot see this branch here anymore. So what you find out is IL0 plus, all right, would be equal to IL0 minus. For continuity principle, we talked about that when we started this class. And then that will be IL0 plus plus IL0 minus, and then I10 minus. Both of all these three will be equal, and that will be equal to 5 amperes. If you flip back the slides, you will find out that we found I1 to be 5 amperes. All right, I1 is 5 amperes. This current here flowing this way. So for continuity purposes in the inductor, IL0 plus will be equal to IL0 minus, which will be the same thing as I10 minus. That is how we got our 5 amperes through the inductor. Also, our V10 plus, okay, V10 plus will be equal to V10 minus, which will be equal to 8 volts across the capacitor. All right, this capacitor here, don't forget, if you flip back here, we found V10 minus across the capacitor is 8 volts. So that would also be equal to V10 plus, okay, across the capacitor here. All right, so we said that we've gotten our IL of 0 plus 5 amperes, we've gotten our V1 of 0 plus. All right, so now we want to find our V2 of 0 plus. How do we find V2 when the time is 0 plus, after the circuit is now open? We are going to apply KVL to the entire circuit. Minus V1 for KVL. If we are going this way, we are traversing from negative to positive. Minus V1, and this is going to be V1 of 0 plus, by the way. So we have V1 of 0 plus. All right, and then we go on to this place. So the current that we're passing through this place, these guys here, 1 plus 1 is 2, 2 and 3 are in parallel. So the current that we're passing through this place will be the inductive current here, current IL. So you have this will give us plus, this will give us plus IL of 0 plus, IL of 0 plus multiplied by this parallel connection, which will be 2 times 3 divided by 2 plus 3. All right, so this is multiplication, and then it goes here. You see, you can see that we have 1 here. So this is also going to be plus 1 IL of 0 plus times 1, right? IL of 0 plus times 1 ohms. Okay, we're going to have that. This is 0 plus here. And then we have, since it's KVL, it's also going to be plus V2, isn't it? This is going to be plus V2, all right? Everything must be equal to 0. So if you check it out properly, if you make V2 the subject, everything here, their signs would change. So your V2 will just be equal to plus V1, as you can see, plus V1 here, minus this entire stuff here, then minus this entire stuff, because all of them will just cross over this equal to the other side here. So this becomes plus when it crosses over, this becomes minus, this becomes minus, and then when you apply our values of IL into these expressions, you have 2 times 3 is 6, 2 plus 3 is 5. So this is 5 times 6 over 5. So this gives us just 6 left here. We have V of 1 here. V of 1 is 8. So we have our 8 here. So what we're going to have here, 8 minus 2 times this is 6 over 5. All right, multiplied by 5. 5 cancels 5. So you have 8 minus 6 already. All right. And then again, minus IL. Our I of L is 5 here. 5 multiplied by 1, because this is 1 for this ohms here. So that gives us 5. So you have 8 minus 6 minus 5. And that would probably give us, minus 3 volts. Okay, that will give us minus 3 volts. So V2, okay, after the switch has been opened, V2 plus, after the switch has been opened, will give us minus 3 volts.